Good morning, everyone. My name is Bruce Champagne. My team members, and Vincenzo Alpano and Antonio Simones, and we are T2 FreeEnergy. Our project is highway wind turbine, and our advisor, Dr. Basil. This is just an overview of our project today. We are intending to capture wind from fast-moving vehicles on our highways in order to turn a turbine resulting in generating electricity. Highway is a near source of constant wind energy. With a number of fast-moving vehicles, you're going to see us go through our selection process where we decide whether to use a vertical versus a horizontal. And when we chose ours, we chose a vertical, and we had a hybrid system where it's a Darius combined with a solenoid. The major components, as you can see, and this is the reason why we were trying to do something with regards to renewable energy sources, because you can see from this map, this is the map of Iceland, and right here you realize the depletion of the ice over time. Now look at the amount of carbon dioxide that is generated to produce 1 gigawatt of electricity from renewable sources, and in using fossil fuel, we were able to you're producing 120 times more just for the same amount of electricity. This is where this industry is growing most in the world today. Europe, North America, Asia, with China leading the way with 26.8% installed at the end of 2012. However, this still only accounts for 3% of our energy production.
Our design consideration, what we can take on consideration our design algorithm speed of vehicle, the noise, the birds, the environmental impact, and also multi-language manuals and label. This is our project timeline. So we spent a lot of time doing the simulation and then the solid work modeling.
Okay, and we also did a design survey. The idea to do highway wind turbines is not entirely new. We like to take credit for it, but no, there were a couple of other students that did do the same thing. An architecture student in particular, Joe, calculated that with vehicles moving at 70 miles per hour, it could create 9,600 kilowatts of energy. We don't trust that because he's architecture. But these are just a couple of designs that we looked at before going ahead with our design. Now, as Bruce mentioned, selecting a wind turbine was a very important design consideration, because normally what you see is the horizontal wind turbines. And they're about 40% more efficient than the vertical wind turbines, which we actually went ahead and used. But for our particular application, the vertical axis wind turbine actually makes more sense because rotation starts at lower speeds. And also all of the major components could actually be stored at the bottom of the turbine, as opposed to at the top of the turbine. Now, after we selected the type of turbine, there are subtypes. So then we looked at the different types of vertical axis wind turbines we could go into. The Darius, again, is 10% more efficient than the Savanoid. This is the Darius, that's the Savanoid. It's 10% more efficient. We can't go with that one because it does not start. And the cars, it does not start immediately. Once it gets started, it's more efficient. So we needed to actually use the Savanoid to get it started, because the cars don't come constantly. They're stop and go, so we need something to get it started as quickly and efficiently as possible.
Now you can look at what my team member Antonio just said. We're using the solenoid and the Darius. Here is a proof from this graph that it is more efficient than the solenoid, and we are using it for the reasons he explained. Now, we recognize from research that the wind speed on a highway is between 3 and 10 miles per hour. Now, the wind is most important to our project, which is a cubic factor in our wind, because that formula, where we have the density of the area which is the swept area of the turbine, and the velocity, which is the cubic function, is most important for our on our project to generate enough speed to get power.
Okay, for the Darius blades, as we were discussing a little bit about earlier, they're basically modeled as airfoils. They operate on the Bernoulli principle with the shape of the airfoils actually creating lift and getting us to turn those blades at a certain angle of attack. These are pretty much schematics of what the Darius blades look at. We looked at these 3 different types of airfoils. Those are what airfoil shapes look like. We went with the NACA 4415 basically because it was easier to manufacture and an angle of attack of 4. This is a SolidWorks simulation of our airfoil. This is the actual cross-section of our blade. And this is how it's modeled. Again, it validates the Bernoulli principle. We use 5 miles per hour and a 4-degree angle of attack. And once we selected the blades, then we had to choose how many blades. So we chose 3 blades because 2 or 3 is industry standard, but we chose 3 because it resolves issues with vibration, noise, and starting. And also, when we talk about wind turbines, you'll see them talk about tip speed ratio. And it's because if the blades move too slowly, the wind will go right through the blades. If they move too fast, it's like wind going towards a solid wall. So we need a tip speed ratio for 3 blades of around 4 to 5 because that would increase the performance of the wind turbine. And basically facts and figures, you'll see this at the end of all of our components, how much it costs. The force calculated on the blades was a lift force of 0.34 pounds, a drag force of 0.008 pounds. The material was aluminum. It needed to be lightweight with foam interior, and it's 2 feet in length for the blade.
This is a solenoid section of our blades, and most solenoid sections of turbines you will see those only have 2 sections on either side. However, that makes it very inefficient because if you're collecting wind from this direction, the wind is hitting this side and also hitting that side. Therefore, they are notorious for being inefficient. However, with this design, we are actually recycling the air, helping the same air that is entering this side to return and push that side, giving us a greater efficiency in our turbine. Now, this is a SolidWorks modeling of that using the exact material that we made our blades from. 5 miles an hour, you can see a higher velocity wind entering, the wind return, and at its exit, the wind velocity is drastically reduced. And this is some of the us manufacturing our parts, and they are 19 inches in diameter, and they are made from aluminum and plywood.
This is our thread, which is all the color with the Darius blade. And then it has like a length of 18 inches with 2 inches thread at the end. And then it has a minimum tensile strength of 42 kpsi. And then in our case, we only use 4.4 kpsi and with a factor of safety of 10. And then we use aluminum as our material. This is our color, which has like 3 evenly spaced thread holes with the same dimension with the thread, the one I just showed before. And we also use aluminum, and then the radius of it is 0.75 inches. This is our shaft. That's our maximum stress. This is our displacement, which is a really very small displacement because we have like a huge factor of safety, which is 1,637. In our shaft, we did use like 2 loads here and here, which is the color, but they cancel each other out because they are symmetrical.
Okay, and basically the bearings were driven by the size of the shaft. So we pretty much chose bearings that fit our shaft. They were steel bearings with a cast iron mount. They were rated for 193 pounds. We needed 28.18. We rated them for about 10 years, and they will work with 99.9% reliability. Okay, generator, of course, was a very important aspect of the design because we need to produce power. And we also needed a generator that would produce as much power with low RPMs. Again, these cars don't produce when moving very, very quickly. So we actually bought 3 different generators. The first one we couldn't use because it needed too many RPMs. This one we ended up using because it creates 12 volts of electricity with 150 RPM. So this actually worked. The only negative thing about this generator was that it required a very high torque to get started. Okay, and once we chose the generator, we wanted to amplify the power, so we went ahead with a gear design, and we wanted to go as simple as possible. So the maximum with a set of 2 gears was 10. Was a gear ratio of 10 to amplify it 10 times. But when we calculated interference, we couldn't get 10, we got 5. With the next set of gears, which was this one and this one, which gave us an amplification of 5. And basically we did some system dynamics modeling of the system. We simplified everything to see how the system would behave. We use Rungi CUDA here in the code to go ahead and analyze the system, and it basically told us what we already knew, which is if you increase the RPMs, you increase the current. And
from our testing, you can see a few pictures here while we were testing our device, because we had to return our generator because it was defective. Now, right here, we can see us testing it from our turbine connecting directly to the shaft, and we're getting that reading at 7 miles per hour, approximately 7 miles per hour wind. And these are some other components that we use, a pedal tube, to test our wind velocity versus that other equipment. Pedal tube proved to be much more effective and much more accurate than everything else. And those are some of the readings that we got out at different RPMs. This is actually our project, what it looks like, and that is the generator connected to it. This is just a SolidWorks modeling, and a total price tag of about $608. And this is actually it in the lab where we're doing the testing. We decided to make a small video to show how it operates.
This is our actual cost, where we spend much of the money on the aluminum sheets, which is when I have 3 of it, costs $8.40, and the generator, which costs like $156, and the gears $106.22, and the total cost come up $621.48. That's all manufacturing parts. That's me right there in the tray for the tray. That's Antonia, and then that's the wood that we use for the 7-nose blade, and then that's.
You use a pointer so we can see the slide. I've said that 2 or 3 times already.
Yeah, that's how we made the use blade, and then this is which right there taking the RPM of the wind.
And basically, we would like to get more data on the wind patterns of vehicles to go ahead and optimize our system. And we'd like to see the effect of a collection of our turbines to produce, of course, enough energy to power the street lights at night. We need to look into an energy storage system so we can save the energy toward the day and use it during the day. We can save the energy generated by the turbine during the day and use it at night to power the street lights. And we believe our design is very easy to repair and maintain, and it will have a positive impact globally and environmentally.
Thank you.
All right, Q&A. Who wants to start? Dr. Tamonte.
Okay, I noticed that you did a bunch of analysis on the Darius, looking at pressure isotherm, isolines, and airfoils and Bernoulli modeling. My question is, you didn't present that for the Savinoy design. How would you anticipate it would be different?
Well, for the Savinoy design, we actually did the one where we
You did a
right. We did the fluid flow. We
air flow.
only did the fluid flow because we were mainly concerned with the Darius at first because of the efficiency. And as far as pressure going through these blades, I don't. As far as pressure going over these blades, actually the air goes straight through these. It goes straight through here, so I would anticipate maybe an area of higher pressure towards the back of the blades, but I didn't feel like it was very necessary.
Actually, when we first start testing our device, we ended up putting on just the Darius blades at first, and we realized
You couldn't get there.
the start. Now, after we reached that stage, we realized our angle of attack was very key. So we had to work on that issue. But before we even get to the angle of attack, we added the Savinoy section. And as you put it outside, there it goes, without a car passing that, which is very very good for our case. And then we realized that, oh, this is really good. And when we tested it, we realized that it produced enough torque, even with a defective generator that you could barely turn with your hand. It was able to turn that and generate enough, generate some energy.
Okay, then the other question I throw at you is the 3 generators. Why did you buy 3 generators versus do some calculation and analysis to determine which would make the most sense?
Okay. The first generator we bought was a altered car generator. It was very cheap. We were paying for our own project, so we were assured by these people that they could provide they could provide a generator that would meet our qualifications. And when we got the product, they didn't perform according to what they told us. So the first generator, like Bruce bought, was an altered car alternator. It required too many RPMs. We could not use it, but it was easy to spin. The second generator, it was very hard to spin, but low RPM. And again, the person we bought it from assured us that it would be very easy to spin, and she said it wasn't effective. We ended up having to return it. We actually have a third generator that we got off of a small vertical axis wind turbine, and we were like, okay, since it works with this turbine, it should work with our turbine, and that's what we ended up with. But it wasn't a matter of like calculations, it was mainly a matter of false advertisement for us. But it didn't cost us too much because we returned them and got our refunds without a problem.
That's you, Mr. Dr. Basil?
Sure. So you guys did individual analysis of almost every component on your design, right? But what we're missing a lot is integration of all of those components and analysis together, right? So for instance, it was mentioned before, using, say, flow analysis to then try to predict power output, right? You guys did a systems dynamics type of calculation. Did you see any correlation between your calculation and the actual power generation that you got out?
When we did the theoretical calculations with the 150 mile per hour winds, and we tested the turbine.
Okay.
When we tested the turbine and we got the graphs that we got towards the end, it did correlate with the, not this one, the testing. Yeah, okay. When we did the wind speed versus voltage graphs, it did correlate with some of the facts and figures we got with the theoretical calculations.
So what I would do then is put that on that slide, of course, right? So this is our predicted output. This is what we actually got from the wind turbine. We feel good in our specific simulations and calculations that we did. So that way, we understand that you made those specific calculations and that they were correct.
As a segue to that, and I don't mean to cut you off, Dr. Basil,
No, that's fine.
I have an interest in knowing what the overall efficiency is in terms of kilowatt hours of power provided. Like conventional wind turbines operate at about 30 to 40% efficiency. I'd be curious to know what the efficiency is on yours. Did you figure that out? And this would be a good place to put that kind of efficiency rating. Do you understand that?
Yeah.
Okay. Go ahead, Dr. Basil.
Sure. Lost my train of thought, sorry, 2 seconds. Oh, the other thing, yeah, that's what I was gonna say. So were you able to power any devices afterward? I know we talked about that a little bit, but could you kind of connect up an LED or something like that? I know you're close to that, but.
We bought the light.
Right.
And it should have been able to easily power it because we got 5 volts. At one point we got 6 volts. This is without gears. So we bought the light. All we had to do was attach it, but we didn't get to that point. But we are certain that if we connected the light that we bought to this turbine, it would work.
However, with this device, the storage device is very, very important because we need to store it. We cannot, it is not wise to just use it directly because it will keep fluctuating. However, we did not get to that stage because we had so many issues with our generator. If we were able to store our energy, then we could light something and then everyone could see the beautiful light shining.
Okay, that's it for me. Anyone?
Okay,
Yeah.
I have a couple of questions. First of all, with the infrastructure that you'll be installing to get those wind turbines to attract the most energy from vehicles passing by, that infrastructure seemed to offer another opportunity for you to have solar panel installed on the top of it, so that you could make this a little bit more hybrid, more diverse and all of that. I don't know that would necessarily increase the scope of your project. Have you given that any consideration?
We intended to compare the amount of kilowatt hours generated from our device over a certain section of highway, for example, a whole mile, versus a solar to see what is more efficient in our in using, whether to use the turbine, but we did not consider combining
That
that.
hybrid, yeah.
Right.
That's something worth considering, don't you think?
Yeah.
Because you're catching both natural resources to generate energy. And that could certainly light up a lot of street lights, traffic lights, and all of that, which will minimize our consumption to the other energy sources. Right? And then you could feed that right into the same storage device that you're considering.
Right. So we would connect to the grid.
Right. The other issue is you demonstrated your timeline, but I did not see the division of labor related to that timeline.
We do have it on the report. We kind of did a lot of things together. We kind of did a lot of things together. I know Bruce did a lot of the manufacturing because he's really good at that sort of thing. I did a lot of the solid works and a lot of that type of analysis. Gitchens pretty much was everywhere in terms of helping with the report and solid works and manufacturing. We tried to throw some pictures up there to show that we kind of did everything together and try to feed off of each other. So we didn't really add it to the presentation because it was really teamwork.
Okay. Well, it's a good idea to demonstrate that.
Right,
that
okay.
One person didn't carry the lion's share of the labor. The other thing is, I did not get a solid impression about how you dealt with global issues. Is there a slide there that speaks to that?
The first couple slides we had.
Let us see that again, please.
Next one. Okay. Yeah, those first 3 slides we talked about global warming and the market forecast for global energy and carbon dioxide emissions.
Okay. All right, that's good. That's my questions. Any other? Okay, well, thank you very much.